Such a wild assortment of students this year.
Huh?
You say it's such a wild assortment of students.
Fine. Yeah.
It's recording. All you, I'm sitting down.
Hi everyone. Welcome to our second workshop. This is the circuit analysis workshop. Your hostess today is me and Shawn.
Spell your name wrong.
That'll be
Maggie.
Oh, pretend that's flipped.
Are you guys recording?
yes.
Let me check. I want to make sure the mic's not muted or anything. Alright, we already. I'll check for you again, but thank you, sir.
Alright.
Okay, you're good. Alright, you guys go. I'm gonna sit down.
I can spell my own name.
How can you do that?
That's okay. It's okay.
So they just press it.
Go.
Okay, the basics of electricity. All right, what is electricity? Electricity is a form of energy, and there's two types of electricity: static electricity and dynamic electricity. Static electricity can be a type of electricity that is non-moving. So, for example, there is a magnetic field on everything. For example, this microphone right here, there is electricity pointing out, but we cannot see it and we cannot use that. And dynamic electricity is a flow of electricity. So from one wire to another wire, that will be a dynamic electricity. And electricity can be used for many things, such as generating power, for example. Okay, why electricity? Well, many years ago, scientists have discovered that electricity is the most efficient way of transporting energy, because in theory, the electric potential between one point of a wire to another point of wire is constant. So that means the potential energy from one point of a wire to another point of a wire will be constant. That while if we don't account for any friction. And electricity is also used for many engineering applications too, like robotics, vehicles, spacecraft, data planning, and computing. Okay, current. So if you want to visualize current, you can use water as an example. So so let's say we have a river that is flowing water through from point A to point B. And the higher the current, the harder the wires. So if like the river has really high current, then the water will overflow and then it will cause trouble. And high current is enough to kill you. So 1 amp is enough to kill you.
Recording in progress.
It was.
Okay, and there's multiple types of signals. So like low level signal devices and high power devices. Okay, so why current kills you and what is going to kill you? So here's an example. So basically, okay, let's say a truck coming at you at 60 miles per hour. Will that kill you more, or wind coming at you at 60 miles per hour? So his theory, voltage is a form of force, right? So the voltage is another reason why current will be high, because voltage and current are proportional. So in circuit analysis, we have multiple forms of voltage potential and node voltage. Okay. Ground, okay. Ground can be served for two purposes. One is for electricity to go somewhere, and another reason is for us to be safe and grounded, so that electricity don't flow into us and kill us. but also the ground can be a reference point. Okay. All right, resistance. So let's say in the circuit, you want to control how many, how much current goes into a device. For example, if you want to power a light bulb, for example, you don't want too much current going into the light bulb and killing it. So that means you gotta use a resistor to resist current and so that the LED can power on. And that's the formula we use to calculate how much resistance we need in a circuit and how much current will flow through the circuit and what voltage we need. And resistors can also be used as a load device because you can calculate the amount of power going through a resistor. So if you want to test, for example, if you want to test like a solar panel out and you want to know how much a solar power on the solar panel draws, so you gotta use a resistor to see how much power that solar panel is drawing. Resistors. Okay, I talked about it already.
Huh?
Wait. Okay, I talked about it already. Oh yeah, also resistors can also be used to redirect signals. For example, in later when we're designing logic gates, right? Like all electronics are dumb, and like we don't like they don't know like where the electricity is flowing, so we can use a resistor to direct the electricity. Okay.
The capacitor will short itself.
No,
itself because it's too
not
quick.
yet. Not yet. Okay. Thank you. Okay. Capacitors are a charge device in the circuit. So for example, if you want to power a light bulb on and you want to switch off, you don't want the light bulb to immediately switch off because that's not good for the light bulb. Same thing applies for electronics too. You don't want electronics to just power off immediately. So we have something called capacitors. Capacitors are kind of like batteries from which they store charge on one metal plate, and then when the circuit stops flowing, the plate will discharge any electricity from the capacitor to the rest of the circuit. And like I said, it can be used for noise reduction too, because the voltage, not the voltage, the current flowing out there is the capacitor is also, it flows better than what comes out of the power supply.
Yes.
What are some like real world applications of capacitors? Where can we see them used in like everyday life?
Well, like I said, if you want to power off a LED or a light bulb, for example, you don't want the light bulb to completely shut off right away.
You talk about capacitors in terms of their ability to store charge.
To store charge. Oh, I think I said that already.
Yeah, but mainly the important part of capacitors is when you learn about them, they're kind of like batteries, right? Where they can store charge, they can discharge. But in the real world, they're used to as a method of discharging at high currents, right? They can't store as much charge as the battery, but they're used to, they're used to like start cars. They can be used to start circuits, and also they can also be used as filters as well, right? Because they absorb changes in current in the circuit. So if stuff changes, then I think that's the most important part about at least using capacitors in real life.
Okay.
So let's watch a video of if you overpower, like overcharge a capacitor. From Chris.
When the metal plates touch, they will short each other, and the current in a short circuit will set itself to infinity. However, this power source is currently rated at 10 amps when we do that. I'm just going to stand back here and turn this off so it doesn't flow. All right, buddy. Here we go. 3, 2, 1.
Yeah.
Oh my, alright.
I crazy. Yes.
So when you choose a capacitor value, you wanna choose it so it's the right size and the right energy for your sister circuit and stuff like that, or else this might happen.
Well, the capacitor will short itself on itself because
Fun fact, the reason why that happened was because that capacitor was a 10 microfarad 25 volts, or sorry, it was 12 volts, and I put like 20 volts through it.
That's
So I overvolted the capacitor. It couldn't handle that much voltage going between its plates. And it blew.
right. Okay, and inductors are similar to capacitors, but they store energy in magnetic fields. And we use inductors for many tasks, such as motors, because all your motors uses inductors and magnetic field to spin. So things like microwaves also use inductors because inductors can heat up and it can give power to the microwave. Light bulbs, solenoids, and wireless charging also use inductors because you can use a magnetic field to charge devices such as a phone too.
What is an analogy you could use to describe an inductor?
Water wheel.
Water wheel. So how does that?
A water wheel. Okay. I mean, you can also see it like similarly to a capacitor, for example, because when you turn off a device, right, you don't want it to turn off like right away. So the water wheel will continue to spin until it will slowly turn off.
Yeah. So in electricity, you have three major components, right? You have current, you have voltage, and you have resistance. In capacitors, it stops voltage from changing instantly. In inductors, it stops current from changing instantly. So the reason we use the water wheel analogy to explain inductors, imagine like a big water wheel on top of a river, and people have used this for a long period of time to generate electricity from this water wheel. If you get the water wheel moving, it has a lot of inertia. It's really, really hard to stop this water wheel. Same for an inductor. If you get it going using current, it's really, really hard to stop it. And if you do stop it very instantly, it's going to cause either a voltage spike or a current spike, because again, voltage, current, and resistance are all related to each other.
Okay. All right. Diodes. Okay, so diodes are like devices that you hook to the circuit so that electricity and current can only flow one way. So for example, if you wanna plug in device with two terminals, for example, and if you mess up the positive and negative terminals, a diode is there so that the circuit does not break. And at the modes, forward bias, it allows current to flow through one direction. Reverse bias, meaning that you prevent current from flowing into another direction. And breakdown. So basically, breakdown happens when there's too much voltage applied to the diode, and it will just break and it will become useless. But in a lot of electronics, when the diode breaks, the circuit will open circuit and then it will just stop working.
You will, at the end of the lecture, we will do simulations, so this would make a lot more sense later on.
But funny story, actually. When I designed Wiki-Learner 1, well, when we did the first ever soldering workshop like 2 years back, I forgot a reverse polarity protection diode in the circuit. So about 30 or so kits did not have a reverse polarity protection diode. So if the students, when they were building the kits, they swapped the red and black wire, the chip would just, the 5-5 timer would just blow up. It would just like start smoking. And that's like the danger of electronics. Fail safes are very important, and diode is one of them. So if you put a diode there, even if the user decides to be stupid and flip the wires, the current will not go in the reverse direction of the diode. So it'll be blocked from going the wrong way and destroying stuff in the circuit.
Okay, transistors. So transistor is basically a switch or amplifier. So let me just draw one up. Yes. Okay. So you have electricity coming from point A to for example point B, right? But then you will have a transistor right here. Let me draw it out. Okay, that's correct. Okay. Okay, so okay, and this is point C. So like if you don't have any current going in right here, that means current cannot go from point A to point B. But if there's current coming in from point C, that means current can go from point A to point B. This can also be used as an amplifier. So so for example, if you for example, if you send a noise right here or like a signal right here, and then you want that signal to be broadcasted, you can use another source of power to help it with that. So just send a signal in right here, and then you will amplify. So that's what a transistor is. And there's two types of transistors. There's one called BJT, and that's a current controlled switch. And that's good because it's low powered and you can do everything you want on it. And field effect transistor FET, that's a voltage control switch. And one thing good about the voltage control switch is that it will switch really fast. So it's good for CPUs, for example, because those things go up to the gigahertz, I think, and then you need it to power on and off. But those things use a lot of power. That's why CPUs get really hot.
All right, so earlier we talked about the polarity, right? When you plug in a battery, you know, there's plus and minus. If you plug it the wrong way, it could blow up, like Chris said. So this is a Arduino Nano. Yeah, it's a Nano, and some chips already, they have protection on it. So on here, it already has a reverse polarity protection on it. So there's a Raspberry Pi, but a component that doesn't have it is the ESP32, which is the module to connect to the internet. So that you would have to put yourself. And again, later we'll learn how to do this.
By the way,
Yeah.
sorry, if you do decide to test this out on Arduino, the Arduino, which is a miniature computer, has status LED. You'll see those flicker if you try to do any funny business with them. Now, generally, when you're working with Arduinos, you want to make sure the system is turned off before you switch some wires. But a lot of students will be impatient and decide to like put something where it shouldn't be when the circuit's turned on. And sometimes that can really lead to a short. And Arduinos don't like shorts, so it will turn itself off to save you. But not electronics are like that. If you're taking 3301, the PIC won't do that for you. The PIC will just blow up.
Okay.
Yeah.
What is the protection? Like, is it another layer on the board?
It's they have, so in the next few slides, you will learn that there's multiple ways to protect it. So earlier we talked about the diode, and you can also use the transistors too. I don't know what's on this one.
There are multiple ways. Diode's the easiest one. So like if you include a diode in your circuit, it'll basically prevent any current from flowing the wrong direction. So if you do reverse polarity. But if you have too much current, there's also a chip that can detect that and just shut off the circuit for you. But like Maggie said, it's generally a transistor that controls like the power going to the circuit. And if there's something wrong going on, it'll just break. So it won't allow any current in the circuit. And when things are fine again, it'll connect back together. But the next slides do show, if I remember correctly, different types of ways you can connect the circuit.
Yeah, so funny story about blowing stuff up. So at work, when I interned, there's the plus, pretend this is the plus, pretend this is the minus of a LiPo battery. And LiPo battery, the one we had was like 20 something volts, right? And he had two connectors connected to the battery, and then he touched them together. He shorted it, and then the battery blew up in his hand. So then he got a second degree burn. So it's very electronics is really cool, but it's like super dangerous. So you have to have a lot of protection, right?
What's a LiPo battery?
Lithium ion.
Polymer.
Oh, polymer thing.
Yeah. So lithium polymer batteries are one of the most insane high current batteries you can get. They're used for drones and RC cars. Most lithium polymer batteries actually come built in with the BMS, which is a battery management system, to protect yourself from shorting it out.
Yeah.
But since it's made for high current applications, it doesn't account for something like that happening. High currents make stuff get hot really fast.
All right, cool. So this is the first method, the diode method, right? So again, a diode, if I were to like draw it here, right? So you have in, and then you have the diode, and then you have out, right? So thankfully, the diode is super nice, and it tells you the direction of where it's supposed to go. It's an arrow, right? So when you plug in the volts, the plus, it will go, so it will go through this arrow and go through. If you were to plug it over here, right? If you were to plug the battery on this side, it's gonna hit a wall. And you know, electricity is not like us where it can jump over that wall, so nothing will go past, right? So that's the whole purpose of a diode, where it stops the current going from one way, or it lets it go the other way. Or also important is that the diode is not nice. It's nice, it has the arrow, but it costs you a little bit of voltage. It says for you to go by, you have to give me 0.6 volts average, typically. So it does have a voltage drop if you go from one side to the other side going through a diode.
Yeah. Also, LEDs can also be diodes. They are a form of diode.
Why is the voltage drop bad?
Because sometimes it loses, you know. It loses the. Okay, so sorry. So it might be bad because sometimes you need that voltage. There, in the next circuit, you learn that.
Can I show?
Yeah, sure.
Okay. Okay. Okay, guys, here's the graph for a diode. Okay. Okay, so let's say let's say that's volt, and like in order for a diode to work, it has to be that amount of volts. But why? Because for example, this is VN, and V for example, right? That's time over. So here's the graph of diode. I think that's okay. Yes, currents. Yes, currents.
Yeah.
Okay, currents. Right. Right, because if there's a negative current going in, that means there will not be any voltage. I mean, okay.
Current's also on the y-axis. What he's trying to draw is the voltage current characteristics of a diode, which if you're not an electrical engineer, you don't have to know this, but it just explains how when current changes, how voltage changes and vice versa. But I think because I was the one who created these slides, the reason I put this here was to explain how, if you're doing a project, why this would be very traumatizing for you. Let's say you are doing a project that uses a 3.3 volt cell battery, it's like about this big, and you put a LiPo there. Let's say your chips, your IC chips, or whatever you're trying to power, runs on 3.3 volt logic. If you put a diode there to protect your circuit, you're losing 0.7 volts from 3.3 volts. You're getting 2.6 volts on your IC chips. And that's not enough. You're lowering your voltage on your circuit. It's kind of like starving yourself of food. If you're starved of food, your brain can't think. If the IC chip is starved of voltage, it can't think. So it's really important to ensure that your circuit is getting the right amount of voltage based on what you're trying to power your circuit with. Because with all projects, you're going to need, power source if you're doing something electronically, right?
Yeah. Basically, period is that you just lose the voltage, that little part of the voltage.
Now, sometimes you don't care about that. For example, Blinky Learner. Most of those chips on a Blinky Learner run at 5 volts TTL. TTL standing for transistor logic, right? If I power my system with a 9 volt battery, and I use a diode, which will make the circuit's VCC or voltage cover collector voltage at 8.3 volts, that's okay because it's more than 5 volts. Now, of course, if I'm powering this with a 9 volt battery, at some point it's going to deteriorate. It'll actually deteriorate faster and get lower than 5 volts and can't power anymore using a 9 volt battery. But just generally, diodes are cheap, they are effective, but you need to know when to use them, when not to use them.
All right, so this is the second method, which is the PMOS method. Unlike the diode method, there is no voltage drop. I believe so.
Very little.
Yes, no voltage drop, and it's like very minimal, right? So, earlier we learned that the PMOS is a voltage, or a FET in general, is a voltage regulated, like voltage controlled. So if I were to draw this, circuit here, actually I can show you. So right now, the voltage plus is going into this, pin right here. And through that allows it to go through because you're going straight through and ground is putting it into this one. So a PMOS to turn on that system, right? Right? For a PMOS to work, this gate right here has to be like less than or like 0. You can say 0 has to be less than these two coming out. So if we have 5 volts in here, and this is to ground, right? That's 0. Then this will go through. The voltage will go through. So why when we put it the other way, it doesn't go through? Because like I said, this one has to be greater than this gate right here, right? So if we plug in -5 volts, is -5 larger than 0? No, right? So this one stays closed, right? And then there's no shorting right here. So there's like, it's like, oh, help, let me through, you know? So if,
So.
Yeah.
That would be in that cutoff region,
the cutoff region,
like,
A simple way to think about it, and it's how I learned PMOS, because if you go into 2200, for those who are not EC majors, 2200 is the microelectronics course. You get a whole bunch of like random stuff being thrown at you, and numbers are just insane. So PMOS and NMOS are in the family of logic level transistors, and when you're using them in projects, most of the time they'll be logic level. That means in order to turn them on or off, you'll use 5 volts or 3.3 volts sent through the gates. It's like the gatekeeper of transistors. If you send, for a PMOS, if you send the gate 0 volts, then it'll enter what's called saturation mode. Those two terminals at the top will connect together. If you send 5 volts through the gate, then it'll close off. It's saying that's too much. I'm keeping it out. And that's called cutoff mode, right? That's when the two terminals don't short at each other. Now, there's a whole lot of other complicated things you can get into regarding transistors. That's the simple way to think about it. If you're using an NMOS, which is like the opposite variant of the PMOS, then it's opposite, right? 5 volts turns it on, 0 volts turns it off. For PMOS here, why this is useful is because when the battery is flipped, negative voltage isn't actually a thing, it's just a concept. But you're sending like 5 volts through the bottom. That's where the important part is. And basically, the PMOS is now receiving 5 volts through the gate instead of 0 volts through the gate in reverse polarity. Right? So if you put 5 volts through the gate, it's going to say, no, that's too much. I'm going to close myself off. And that's going to close itself off to the rest of the circuit. It's going to stop the circuit from receiving that backwards current, which is going to destroy all the isochips.
and when it goes to the active region.
Okay, generally, it depends on the PMOS you use, I will say. If you're using a logic level transistor, generally the turn on region is about 0.7, 0.8 volts. That's like the curve you see on a graph. But some transistors even have lower or higher values. It just depends on the one you use. And, like each transistor has a voltage drop calculated by the internal resistance of the transistor. It's a really small R that's inside each one. But again, if you want to really know the specifics, you got to look at a data sheet. Then you get to the complicated zone of things.
oh, we're gonna build that circuit later too.
Yeah.
Okay. Regulator circuits. Now, this one is different now because earlier we're just protecting the circuit, right? Now we are saying that the input, let's say a good number like 24 volts, right? If you plug in 24 volts into a chip that's working in 5 volts, that thing is like gone, right? It's gone. So we have something called regulator circuits. So this one is the LM7805. And this one is not adjustable. So this is only stuck at 5 volts, right? So this circuit right here, it has 12 volts, but I believe it can go up to 36. But no, not problem. Look at the data sheet. And you plug in a high voltage, right? So let's say you get it from an outlet, you put it in, it's like around 12 volts, right? So then it goes through here, goes through the chip, and then it output 5 volts. Any value you put in the input, it will always output 5 volts. Yeah. Oh, it has its limitations. But so earlier we learned about all the FETs and the MOSFETs and everything, and in that tiny chip is this. And I'm not gonna explain to you this because this is a lot. All right. So now let's say if you want to plug in that large voltage value, but you want specific ones, right? So earlier that other one can only do 5 volts. But these chips right here, they allow you to change the voltage. So you can, for example, the LM317, this one, if you change the resistors, you can actually get a different voltage output. The only important thing is if you input a voltage of like 12 volts, the output cannot go higher than 12 volts.
Is that because you have a bias? That you're biasing that?
Biasing it? I don't know if it's called biasing. I don't know. I don't think it's called. I don't think so.
It's not a single transistor.
Yeah.
It's a bunch of transistors work together. So like at the very high level, you can think about it just doing one function, just like turning the voltage from high to low.
Let's see. So here's the equation, So depending on how much your voltage you want out, you just use that equation using this one. So on all the blinking learner. Oh no, not yet. Go next. So now this is the blinky learner one. So all these blinky learners that I believe many of you have done. There's one chip on here. This one right here. I don't know if you guys can see.
So to pass it around.
Okay.
Yeah.
There's a chip in the middle of, you see these two eyeball looking things, like Mickey eye thing? On the middle one, there is the chip, and that's this chip right here. So that chip is basically a voltage regulator, but now it's the flat one. Earlier you saw it's like the big chunky one, right? The one that you have to stick in and solder it through the hole. This one is surface mounted, right? So same deal with all the voltage regulators. You put it in, this is also the adjustable one as well. So you change the resistor values and you'll be able to output a voltage out that's not higher than the voltage.
So why is higher voltage bad for the ICs?
Because then it will put like too much. It will put too much power into it and too much current also as well into the chip, because sometimes they can't, or many of the time, all the time, they cannot handle all this high voltage and high current going inside.
Yeah. Voltage is the force, right? It's the force that pushes the electrons through the circuit. Current generally doesn't just occur. Some load has to draw current from the system for it to happen. So current's not just there without something to draw power from, like an LED or a light bulb or something. Right? So voltage is really, really important that you keep it in check, because once something needs those electrons to power itself on, that voltage is what's going to provide it. And if you have too high voltage, it smashes those electrons through your IC and blows it up. That's why we need regulators.
All right, so full bridge rectifier. So, for example, this is an outlet. Everyone knows what an outlet is, right? But this is all AC power. AC is like wave, right? So that is kind of what this is right here. So an induction coil is mostly outputting waves, right? Because it's like this. That's how power goes into the induction coil, right? So everything we've learned mostly have been DC power, which is like a battery, right? There's no waves in that. So how do we go from this to DC, right? When you plug in your computer on your laptop, for example, right? There's the big block. That big block or adapter is basically what's this inside that circuit, right? So what happens is it's a lot of like electrical part, but basically you start off with like this sine wave or cosine wave, whatever. And then once you go through the diodes, remember that diode only lets you go into one path, right? So if you follow the path of like positive, this is like positive side, it will flow through one way, right? And then eventually you will get only the positive side. So it will be like that. There's no more negative side. And then with the voltage regulator, it will regulate it because it will output like a little like a line, but it's still wavy, but it's still a line, right? It's not like a sine wave where it's like big, like you know, it's like which is basically what DC is basically like a line, right? And I don't think we'll go over this, but yeah, that's the capacitor. Yeah. So yeah, that's, oh my god, I almost forgot that. Okay, so the diodes are going like this, right? It's getting the this negative side, bringing it up here. The capacitors, what are the capacitors? What did we learn about capacitors? Capacitors store energy, right? So when it's going from when it's like going charging up, it's also discharging as well. So eventually the circuit will look like, right? It's not fully discharging because it's not fully going all the way down because the capacitor is adding voltage into it, right? So it's like, and that's like the straight kind of line that I was talking about. I think we will see I made a simulation that will go over capacitor charging. And it'll make more sense when we get into it.
All right, logic gates. Okay. Maggie, marker. All right, logic gates. So why do we need logic gates? Well, if you have a computer, for example, computers are made of millions, if not billions of logic gates. And yeah, so like, for example, if you want a light bulb to be turned on, but you need to press, but the condition is I need to press two buttons to turn on the light bulb, right? So in that case, you can just use a logic gate so that the logic gate can make sure that two buttons have to be turned on. I mean, press for the light bulb to turn on. And the logic gates can either be high or low. So high is usually 5 volts or 3.3 volts, and low is usually 0 volts, and it's always a low power. Okay. AND gate. Okay, let me say AND gate. AND gate, like I said, so like if you want to turn a light bulb with 2 buttons, and both buttons has to be turned on for the light bulb to turn on, use this circuit. So for example, we have point A input and point B output. So AND gate has 2 switches, right? Switch 1 and switch 2, right? Right. So in this case, if you turn on switch 1, right, and the switch is turned off, for example, okay, how did this work? Right, the current still won't pass through because switch 2 is opened. But then if you use another condition from which switch 1 is open but switch 2 is closed, well, in this case, electricity can flow from point A to point B because 1 is open. So AND gate makes sure that both gate is closed for current to travel from point A to point B. And that's the Boolean expression and the truth table. Okay. OR gate. So like OR gate works when at least one input is high. So OR gate works this way. And let's call let's call this A, and let's call this B, right? So like if you close A, electricity will flow through because point B is independent. And if you close point B, electricity will still flow through because point A is independent. If you open both, then electricity won't flow through because both is open. But if you close both, electricity will still flow through. And that's the truth table for it. Okay. A NOT gate. Okay. A NOT gate happens when you input high, but output you want is 0. So a NOT gate it often involves the transistor. So let me draw. Okay, there you go. Okay. All right, that will be ground. And this will be B. And this will be C. Okay, okay. So for example, if I apply a current here, then that means the transistor will be on, right? Actually, let me put this resistor right here. Okay. Okay, so like if you turn the transistor, right? So when input is 1, that means the transistor is on. So then the current going from point A will go straight to ground because electricity flows from high to low, but it will take the path of the least resistance. And if there's some resistance right here, you will just flow right through there. But when C is off, right? That means the transistor is off. So electricity have no choice but to flow from point A to point B. So that's how a NOT gate works. So you always want this to be on, if you want the output to be 0, because it will just go straight to ground. And if this is off, then electricity have no choice but to flow from point A to point B. So this is output and this input, and that's the electricity. Okay.
Basically, if you put in a 0, it'll become a 1. If you put in a 1, it becomes a 0. No.
Okay. All right, and here's a NAND gate. Okay, I'm not gonna draw this one out because it's self-explanatory, but a NAND gate is basically the fundamentals of for computers and SSDs, if you've heard of those in computers. So in the computer, there's billions of NAND gates switching on and off to store data, for example, and that's the truth table for the NAND gate. Okay. And that's the circuit for it. Like, you want to explain?
Me?
Yeah, you want to explain that?
Let's see. So with the other one, we just learned that it was 1 input, 1 output, right? In this one, this is 2 inputs now, and you have 1 output. So let's see. We have VDD, which is ground. No, VDD is positive, VSS is negative.
Okay.
But basically, using the same like ideas with the MOSFET and the MOSFET, whenever you have a signal that's 1 or 0, right? When you put in 0 or 1, I just said that, but it will turn on or off the switch depending on what your initial like input is.
VDD is positive, VSS is negative.
And
VDD is collector supply, VSS is storage supply.
okay. Okay, and here are the different applications that you can use for NAND gates. Okay.
When we use these logic gates? When do we use these logic gates?
When we use these logic
Yeah.
gates? So these logic gates are pretty helpful because when you see those chips, when he was talking about 555 timers, or when he was talking about, when I was talking about like our, what's it called? The blinky learner, all of those inside those, so on here, they have stuff, like a shift resistor, right? All of these like, chips and stuff, they all have these NOT gates these different type of gates, right? So if you ever look on the computer, on YouTube, somebody actually used ton of these gates, like OR gates, AND gates, all of them, they put it all together and they actually made a computer, like a CPU, So you're using these gates, and these applications are the basic fundamentals of like building a CPU, building a computer, or all these type of chips later in the industry.
I have a question. Does anyone here ever play Turing Complete? Or know what it is?
I'm curious.
Turing Complete is a game where you simulate logic circuits and you basically build the components of a computer. You build like a CPU, you build arithmetic, you build memory, like RAM, and then you can write assembly code for it. I think it's a really great game. It's like $15 on Steam. And it's a really great learning experience too. It really shows how these logic gates can, make the fundamentals of a computer. Like when you get to like memory and synchronous logic, things get confusing, but that's really how a computer, for example, can remember things. Yeah, that's what's inside all of your devices right now, just logic gates.
A ton.
Why do you use like NAND gates more? Like, you have like the ORs, for example, that and all of those are with NAND gates,
In this one?
Yeah. Like,
Why the NAND gate?
why the NAND gates?
Why is that universal?
Ooh, there's only ever like 2 real gates in the world, and it's NAND and NOR. It's also easier to build an entire circuit out of NAND or NOR gates, because you don't have to worry about all the different types. You can make any type of logic component with just NAND or NOR. And a NAND gate is built out of like transistors. So if you want to go even further back, that's where that logic is from.
And most SSDs have NAND and NOR for storage if they're universal gates.
And flash.
Oh, and when we were learning all this, there's 2 sides to like transistors. There's the analog side and then there's the digital. Everything in here is all the digital, like one input, one output for the transistors. But there's another side to it when you apply like digital analog.
But it's also like, for instance, like it's digital, but you use analog to make it digital, right? Because if the NAND gates or the gates are built with transistors, transistors are considered to be analog, right? And then we're not.
I really like your train of thought, and the answer is kind of, because like for ECE students, like transistors aren't like binary; they're not 0 and 1. There's like a gray area in between, which is why you can't characterize transistors as purely digital. But they're digital enough so that we can do mathematical operations with them. But sometimes there's glitches inside a computer, and sometimes that happens because transistors fall in between that gray area where they can't operate correctly. That's what happens. It's safe for us to assume that they're either 0 or 1, but the real ones inside of us, if you want to get more complicated, no, that's not true.
Yeah, and with NOR gates, it's the same logic with NAND gates, but it's flipped, meaning it cannot be 101 and cannot be middle of those inputs, and both have to be 0 in order for the output to be 1. And it follows the same logic as AND gates, as all the devices use them. And that's the. Wait, do you want to explain or do you want to move on?
What?
Yeah, thank you.
And
Thank
I
you.
want to explain.
The circuit.
All right. So you have
Not really.
not really.
You don't need to.
Yeah.
That's just basically we use symbols to represent the digital logic, but in real life, if you want to build like an AND gate, you want to build an OR, you need to like construct something like that. Because all those transistors, you see all those A and B and C, where the A and B's are, they're at the gates of the transistors. And if you boil the transistors down to a simple explanation, the gate is what controls whether that transistor is closed or open. So different combinations of A or B can open or close that gate. And if you plug in all the values from the truth table, you'll find out that C gives you the operational behavior of NOR, NAND, or any of the other logical operations.
Yeah, so we can do with NOR gates. All right, here's the XOR gate. So the XOR gate, it cannot be 0 and it cannot be, okay, the both input A and B cannot be 0 and 1. So it can only be 0 and 1 and 1 and 0. Yes. And Maggie, do you want to explain priority checker? Okay.
Odd parity checker is, it's a detector for the odd number of inputs. So you can have multiple input XOR gates. Basically, the amount of ones in the input will determine if the output is 1. If it's an odd number of ones, then the output will be a 1. If it's even number of ones, the output will be 0 for XOR.
Okay.
Does anyone know a more fun application of XOR gates?
Okay.
It's really popular in things like cybersecurity. Anyone here interested in cybersecurity? No? So basically, cybersecurity is the science of protecting passwords and data that you don't want other people to see. And XOR gate has this really cool property of being commutative, which means like A XOR B equals C. And you can do like B XOR A equals C or C XOR A equals B, which means you can create a password and XOR it with your data to create something really scrambled. But if you XOR that data with your key, your secret key, then you'll get back your data, which is unencrypted. So it's like the simplest way to scramble your data and get it back, which is why it's very efficient and liked by many people.
Oh, I've done like hand photography like by hand, and usually when you do that, you use like a matrix for what it looks like. Is that similar to?
Kind of, but in this case, it's only one line. Because the one line is your key. It's your key that you XOR the data with, right? So you can create like a 2-row by however many like column you want the key to be, and you just start XORing it over and over and over and over again. And then you get like a scrambled mess at the bottom that no one can read. But you know, if you just unscramble it using your XOR key, you do the same exact thing, you'll get back your data.
We're talking about the same thing, but okay, cool.
Yeah.
Here's XOR gate. So like what Chris said, but it's the opposite of XOR gate, meaning it will check for even parity. So it will check if there's 2 inputs or not. So if there's two inputs, then it will be 1. But if there's only one input, then it will be 0. But if there's no input, then it will still be 1, because 0 is a even number for computers.
The fun is here now. Ready. So, all right, there's two challenges. All right, so this is the first challenge, and the first challenge is not a challenge, it's us gonna go over it together. So it's a fun challenge we'll do together. You're gonna go over 4 circuits, right? We're gonna go over the diode circuit, which is the protection one. Super simple. We'll explain. You'll see why it like doesn't go through. The PMOS one, which protects again the same idea, but now it's a PMOS. And now we have 2 cooler ones where you have a capacitor discharging and charging. So you'll actually be able to see the capacitor charge up and discharge the LED light, right? And then we have a cool one that I put in, which is the voltage doubler. If you have the AC power, you can actually put it out to 2 times the voltage. Okay. So I know you guys might not have what's it called, Multisim, right? So we can get it on. You can either watch me or you can get it on the web browser. So if you look up Multisim Live, right? Multisim Live. Right? You click on the first one right here, and you can use this for classes too. So like in your 1101 classes or 2101 classes, you can use this. You know, you don't have to have a computer. I think you can do this on the iPad, but no promises. I don't know if it's true, but so you make an account or you don't make an account, or you have to make an account, but I'm gonna log in. Bad gateway.
Yeah. I kind of warned you about that.
I realized that in the middle of the work.
Okay. All right, I wish, maybe I can do it like. I'm gonna hide this. Okay. I don't know, oh, it's this. There we go. All right. So you probably can't see that from here, but the first circuit is the diode circuit, right? So does everyone have it? If you can't pull up on your computer, you could always just kind of like know what I'm doing. 'Cause I'm gonna explain everything. So on the left-hand side, this is where all your components are. If you download the actual Multisim, it will have more components. But since this is the online version, you have basically all the necessary components that you want, right? So first, we should have a DC voltage, right? Because this is gonna act as your power supply. Now, we talked about a diode, so I'm gonna pull out a diode, as well as an LED, because it says we have to protect an LED, right? All right. So what's the rule of thumb when we have an LED? Resistor, right? You don't want to kill that LED, and you don't want to blow it up like Chris did with his capacitor, right? So we have a resistor. Let me do it this way. Right, and we can keep it at 1K. Normally you would use 330, but 1K should work too.
It also scales with the input voltage.
What does?
The
Oh.
resistance and the brightness of the LED.
Yeah.
I remember like testing all sorts of stuff for Blinky Learner to figure out the right brightness, because the very first time I did it, I used a resistor with too low resistance, like 330, and the LED was blinding. It gave me temporary blindness every time you looked at it, which was like not fun, but.
Yeah. Also, you guys have to note that different colors also produce like required different voltage drops. So I think like yellow is less than red, because
Red
red.
is like the most consumed.
Yeah.
I remember a lot of when you get to the circuit construction workshop, by the way, and there's the challenge to light up some LEDs with buttons. You can't, if you use like all red, it won't light up, right? Because there's not enough voltage to supply all those LEDs.
Exactly. So this looks like a diode, right? The LED light. It looks like a diode. It basically is. So if I were to flip this, it will not turn on. But let's just turn it on right now. Move you, get out of my way. And we play. We run this. Wow, the light turned on, right? The light turned on. So this means that the current is voltage, power, whatever is going through that diode, and it's gonna flow into this LED light. And if I were to add a like voltage here and a voltage here, I don't know if this is ideal, so right, there is a voltage drop, right? On this side, on the green side, it's 5 volts, which is your power supply. On the other side, it drops to 4.3. So that means that during that, let me through, it's saying like, okay, I'm gonna charge you some voltage, right? Like I explained the slides. So now what if we change this to a -5 volts, because or here, let me just flip it. Let's pause it, take it out. Oh, it just killed the whole thing. Right? So now I just flipped it, right? So let's say you plugged it in the opposite way. The negative side, which is the shorted side, is gonna go into that diode now, right? Let's see what happens. right? So what we see here is that the LED light is not on anymore because there is no voltage, or it's like negative. It's like going, you know, this is going to ground. It's just like weird, right? That's not right. So the LED light is not gonna turn on. So that's the first circuit. Any questions on this one? No? Good? All right. So now we have the second one, which is the PMOS regulator circuits. Should I just, let me pull it up. On here. I think it was this one. This one right here. Right? So when we build this circuit, we'll see where all the probes are going to be placed, right? So Multisim is really good if you want to probe everything to kind of understand what's happening, right? So let's see. Oh, no. How do I get rid of it? Oh, here. Okay. So let's see. We have the voltage. Let me erase this. Let me erase this one. Let's flip it back to normal, right? So if you want to look for PMOS, this looks like something familiar, right? That's the transistor. So we click on that, and there should be a PMOS, like, yeah, PMOS right here, PMOS, right? And everything is pretty like user friendly because this is like for students, you know, to like use when they're first starting. So we'll flip it around, flip, right? And I'll get rid of the diode. So that diode right in the circuit right here is kind of protecting the MOSFET or the PMOS, right? So in our case, I won't use it just for simplicity purposes. So if I were to redo this whole circuit, right? And are you guys able to follow along on your own screen or no? Is it you guys? Do you guys get it to work? Yeah. Okay. If it's asking you for license, you have to go to the engineer, like CPP engineering software, and just click on Multisim. And when you make the account online, just put the serial code. It's like it took me less than like 5 minutes, like literally like maybe 3 minutes. So it should be pretty quick. Alrighty. Oh, it's so ugly. There you go. All right. So let's take the voltage here. Yeah, the PMOS. You click on whatever this transistor looking like. This is a BJT right here. Right? It says transistor. Oh, you have the app, the download. I think you can look up transistor. Or yeah, okay, yeah. And so we have one here, and we have it here, and then we have one here. So now let's run it. Right? The LED light is on because this gate right here is touching the ground, right? It's directly connected to the ground. So 0 volt is always going to be shooting into that gate. Which means that since this is a PMOS, it allows voltage to go through, current to go through, right? So that's why we have that drop, and then we have the LED light turning on. I don't know why that has such a big voltage drop. Normally it wouldn't, but it has something to do with the information on the right-hand side, right? So now let's change the polarity. I'm gonna do this quickly by just putting -5 instead of 5, instead of like flipping it and everything. We can see that it turns off, right? Because now if you pretend this is plus and this is minus, right? That means that the +5, which is right here, is going into this gate now. Wait, why is it not? Well, normally, so you're going positive into this gate, and then you have the negatives. Oh, no, sorry, ignore me. Not that. You have -5 volts going into this one, right? And remember how I said that the voltage at the gate has to be the lowest voltage But right now, the lowest voltage we have is -5, right? So that's why it's not going through because 0 volts is larger than -5, right? Okay, we finished 2 of them already. Let's see, let's go back down. So now we're gonna do a capacitor. Oh, any questions? Yes? This one? You have to stop the circuit first. So you have to stop it, and then you take it right here on the corner, right here, and then you can click the voltage, and then you want to change the color. You can change the color. But everything is like right here, so you can also get the current as well. So I want to get the current at this point, right? You can also run it. Oh wait, it's not polarity. There you go. Right? Then you can get the voltages and everything. Is that what you're asking?
Where can you get the polarity?
Which one? This thing? Right here. So if I stop the circuit, what is this called? This is a source, right? A voltage source. So right here, this is where sources is, and then it's DC voltage. And then you just put it.
No, I mean like the little numbers we're talking about.
These numbers? When you click it, when you place it out here, it should.
Like the way you change it, like how can you change it?
How did I?
Yeah,
Oh, how do I change this one to -5? I just clicked on this one, and then the value is right here.
and there's positive, negative, right there.
Yeah, the positive and negative right here. Is that what you're talking about? Yeah?
There are specific reason why anyone would build a circuit,
Run reverse polarity, like when you want to put in negative. So yeah, in what's it called? In an op amp, for example. An op amp has looks like this, right? Where you have 2 inputs and an output. Some of them you can power it up like this to ground, and this one to like VCC. But actually, some of them, depending on the data sheet, you have to have negative, like VCC, for it to power on. So you need both the plus and the negative. That's one example of why you might need it. We have the other polarity. Was that the question? Is that sorry? Yeah. Yeah, sure, I got you. I think it would be better to draw it. So. You can see from here? It's not far, yeah. Okay, so a PMOS is this. So PMOS, how it works is this is the gate. Right? Drain, or so this is the official name of this. Source, drain, and gate, right? And so when you are putting in to get the voltage or the current to go through here, this gate has to be the least voltage. So right? The lowest voltage in all both of them. Or it has to be the least voltage here. Mainly this one mainly, right? So if you put in right here, and you put in 5 volts, right? And let's say this is 0 volts. The source right now is larger than the gate, allowing current to go through, right? But if we were to flip the polarity, so if we put in neg.
Like your green source was switched.
Oh, it is?
Yeah.
But it doesn't switch for PMOS?
No, it's just the arrow.
Oh,
Unless this is telling me something wrong.
Okay, continuing on. If you have -5 volts here, right? 5, this source right now, or this drain, this change to drain. This drain is now less than the gate, right? Therefore, it's saying like, oh, the gate has to always be the lower value. So that's why there's no current. It will not let you go past because of this, because the drain is less than the gate. That's basically how this all works. Does it make more sense? Do you have any questions? Like, if you can think of any of them?
Like, should it be VGS instead? VGS is the threshold. I don't know if that's always true. That's not asking.
I know for like how they explained it, it's mainly like usually if this voltage, basically on total is if this voltage is less than this one, then
It's not always true, in
really
my experience. It's better to look at VGS threshold voltage instead
VGS,
of the drain voltage, yeah.
I see.
If VGS is higher than like a certain amount, then it turns off for PMOS.
VGS is the difference between here.
Yeah.
Yeah.
So generally on a data sheet for a specific PMOS, there are like a bunch of different PMOS for a bunch of different applications. You can have like power PMOS, you can have small signal PMOS, and they'll have different VGSs. The way I choose them at least, and I look at the VGS, say I want a transistor logic PMOS or NMOS. And then I make sure the VGS is above like what my logic level is. Basically, let's say VGS is like 2.7 volts. And I can use it for a circuit because any voltage above 2.7 is going to turn on or off. At least in my opinion, that's a better way of looking at it. I don't think I've ever heard of
Really?
drain. No,
Oh, what? Yeah, I learned it like this.
no, I did not.
Yeah.
I learned from experimentation that that's not always true.
Oh, I see. I don't know. I learned it. I learned it like
Yeah,
this.
because what happens if like the drain and ground are not connected? You don't have -5 volts on there. Like if that's not a system and you just send 0 volts to the gates, and let's say drain is like 12 volts, right?
Yeah.
It's if you have 0 volts to it, then it'll still be in saturation. It'll still be connected,
I see.
right?
You don't have an S, right?
Well, let's assume S is connected to ground,
Yeah.
right? We're not going to go into like common emitters.
Yeah.
At least for like at least simplistic logic, if you think about it as like a switch, then this is the easiest way to think about it. But if you're doing like signal or something.
Yeah.
That's not no longer in my field of comfort.
Like
So it was always, I mean, Python taught me as VGS.
Look at Pagnon. Sad.
Python's awesome.
I know. I love Pagnon. I couldn't get him. So maybe that's why I think it's like him. So sad. Anyways. Yeah. Okay. Now we're gonna does anyone have any questions moving on, continuing before I get rid of the circuits? Were you able to get the question you were asking? Yeah? I don't know. Okay. All right. The next circuit is, where did I put it? All right. The next circuit is going to be the capacitor, discharging and charging. So again, you want to think of the capacitor as a battery, right? So if I were to draw here, can you guys see from here? No, yes, no, yes. You guys see this from there, from back? Okay, cool. So I'm gonna draw this right now, and then I'm gonna see if you guys can build it on your thing. And I'm gonna walk around, and if you can't, I guess look at your neighbors. I don't know. Okay, so you have a voltage source, right? This is, I don't know, like 5 volts, right? This is gonna be connected to a capacitor, okay? And this is gonna be connected to a switch. Why the switch? Yes, so right now, there is nothing being charged up, right? Why? Because this is open. This is ground. This is open. So there's no current flowing in here, right? Once we close it, that's when the capacitor is like, oh yeah, I'm getting energy, I'm getting power, 5 volts go through me. Oh, that sounds weird. Okay, anyway. Anyway, so now again, pretend that this capacitor is the battery, right? So if you take this out and put it in parallel, you have the LED light, right? And then, well, again, like he said, you need a resistor. I should have drew it a little bit. Then we also have a switch here. This switch here is needed because if this wasn't here, right? If this was like this, if you were to close it, it's gonna go through the LED light too, right? It's gonna go through the LED light. So we're gonna have this as an open or a switch so that you can see that this will actually start discharging. All right, begin your simulation connection. Here is the switch, by the way. It looks this switch right here. That's the switch. Or you could use this one. It don't matter. All right. And I'll build it fast too. So, just as you're working, meaning you're still looking at the computer and just listening. I'm just kidding. But basically, in an interview, right, you're gonna get asked, what is a capacitor? What is an inductor? Honestly, just answer it. This is the only thing you really have to say. It is a device or a component that stores energy. That's really all you have to say. And if they ask more questions, then are you?
If they ask more questions, speak from experience.
Yeah.
Don't try to come up with something on the spot. Like when I interviewed for a job, it was like 2.5 hours of continuous interviews, which was like horrible. But most of the questions they asked also pertain to stuff that I've done before, so it was pretty easy to answer. And if they answer a specific technical question like that, just talk about what you've done, even if it doesn't really relate to the question. It's something that they can follow up with the follow-up question if they have it. So if they ask what is a capacitor, I would give a general definition of it, and then go into a project maybe where I've used a capacitor before. Yes.
Where was that?
Where was where?
Where you interviewed that?
MIT Lincoln Labs.
Yeah, go flex. Flex it.
Yeah, that's the one.
An interview too.
Be proud of it, Chris.
Make it until you make it. It was one-on-one.
Okay.
So it was like 5 Zoom meetings. I just got out of one and then went to the other one.
Oh, dude, those are the worst.
Terrible.
I hated those.
I survived, and I had a can of Celsius and a stick of high chew for those. I did it in like a really hot dorm room too. So like the conditions weren't great, but I got the job.
That's all that matters.
Yeah.
That's all that matters.
Well, they say that.
Yeah.
All right. So I just made the circuit. Wait, there. Is everyone good to go? Anyone need help making the circuit? You guys need help making the circuit? Yeah. The asylum? Oh, I need some?
Yeah. Yes.
All right. So, I forgot to explain that the bigger the value, the more power it's or more energy it stores, right? So for our demonstration purposes, we're gonna put this to a pretty large value, capacitor value, which this bothers me. Alright. Alright, and once, if you ever take digital logic, which if you're ECD you will, you will have to deal with a pretty big capacitor. It's like this big.
Oh, yeah, I remember that.
Yeah, so, have fun with that. Don't be afraid of it. If you put too much voltage, it might explode in your face. So,
Generally, the big ones won't.
oh, really?
Yeah,
Oh,
the safe capacitors won't blow up. The one you saw in the video was a cheap one from China. The new capacitors these days have protection so that even if you overvolt them, it'll only like seep smoke out instead of like exploding it out, right? And I'm pretty sure the one they gave you in 2300 is kind of expensive. So,
oh, I got it from
and
the.
also for large capacitors, it's also hard to blow them up because for the big one, you would need probably like 200 something volts for it to blow up.
So earlier you, we mentioned that. That sometimes some boards or so don't allow the reverse polarity. What is it that's on the board that allows it? Is it just a separate pathway?
Can you repeat that question? Sorry.
So earlier you mentioned that. Some of the boards still want to certain code don't allow it, but allows it.
2300?
Yeah.
You didn't have a big capacitor?
What is it that allows?
I can show you mine. I took pictures. So when I took this class, the digital logic, I took a picture of huh?
Generally, yes.
No, Sassoon.
If you want to learn more about circuit pathways, you can come to PCB design workshop. And
When is that?
Which software do you?
that is
I use I think Chris teaches KiCad and Altium, but it's just Altium. Yeah, Vicky. I use KiCad. I like KiCad.
You only have design circuits.
Yeah.
Yeah. Yeah, like buses.
Oh, I don't use Altium. I use KiCad. All right. So wait for me. All right, so we're gonna turn this on now, right? So right now, let me put in the color. This thing. So right here, here, and then here. So right now, if I were to turn it on, what would you expect to happen?
Your passive.
The LED blows up.
I wish. But
Oh, wait, no.
nothing happens, right? Because for current to flow, it has to be a closed loop. There is no closed loop on here right now. Everything is, there's openings, you know? So let me turn on the circuit, right? There's nothing turning on, nothing's happening. Once I close that switch, it's charging right now. I don't know if it's because like I have the other circuit, but I'm gonna open it and then you see it discharging right there? Right there. It's discharging, right? That's oh wait, it's so fast. Okay, hey, let me charge it up again. Charging. It's charging. Okay, and then boom. It's so fast, right? That is because that capacitor is too small. So now if we were to make it bigger, right? So let's add another 0 to this. If I add another 0 to this.
It uses engineering notation. You gotta be like 1 millifarad, 1 M.
Oh, I change it?
Yeah,
Okay.
or like 100 M.
1.
Yeah.
Right?
Is that the one higher than U? U is 6, right?
U is 6, yeah, M,
Yeah.
yeah, that's right. All right. Charging, now we're charging.
To put like a probe across the capacitor.
Oh, right. That means I have to stop it.
See, the fun thing about Multisim Live is that it has an on-screen oscilloscope for you, so you can
Yeah.
actually see the time passing and like what happens as the circuit's running.
All right, are you ready? It's charging, it's discharging. See, earlier, remember how it was only like 11 volts? But now it went to like, what was it? It was like at like 6 volts, right? So if I can go, let me see, right here, right?
To cover why that voltage increases at the bottom. Yeah,
Which one?
the voltage here, why this increases. Because you're just putting this as a node. You need a probe to
Oh,
the
wait,
voltage across, right?
can I do that? Can you do that on here?
Yeah.
Oh, reference, here we go, got it. There we go, let me get rid of this one. Probe it here. Right? Wait, does that work? Oh, no, that has to, this one has,
Maggie, do
Uh-huh.
a regular voltage, or actually press that B minus.
oh, okay, well, that's how you do it.
Yeah, there you go.
There you go, it's different on the app, I think. Okay, letting it charge. There you go, discharging, right there, right? And then once it gets to low voltage, the light turns off. There you go, right? So that is how capacitors are charging and discharging. That's basically the explanation of the circuit. Any questions? No? Cool. Close both? Well, let's see. When you close both, what happens is that it's gonna go straight into P, right? Because this is no longer acting as the battery. Earlier, when we opened the circuit, this is saying that capacitor is directly plugged into the LED light, right? But now the capacitor is kind of like irrelevant. It's the shorting. Yeah, this one, the LED light is actually going to be attached to this power source, right? And in DC, no, it's not shorting. No,
It's
it's open. In DC, capacitor is open.
I don't know if this was mentioned earlier, but like one of the most important concepts in electronics is that electrons are current. They'll always take the path with least resistance,
Mhm.
right? So in this case, if a capacitor, one of the capacitor's properties is that it's an open circuit at DC voltage. Like if the voltage isn't changing, it's going to be open circuit, which means we can just get rid of this and it'll still work the same. The current's going to go up and across this LED and into this path because this path has no resistance, right? That's the least resistant part of the circuit. So it goes through here instead.
So it doesn't get inductor to be short.
Yeah, and the inductor.
Okay, so I got two things. One, add on to that, the inductor does the opposite in short circuit.
Yeah.
And two, what acts as the ground is when you're discharging the capacitor?
Or wait, what'd you say?
So when you're discharging the capacitor, I actually wasn't aware it was straight up power the bolt.
That's a good
power.
question.
Yeah,
That's a good question.
What was the question? Wait.
Where's when you disconnect S1 to
Uh-huh.
discharge the capacitor through it, where is the ground?
So
I'm asking,
you kind of think of this C, there's polarities on capacitors.
right,
If you use one in the lab, there's a plus and a minus. So I don't,
In this case, it's not really accurate. So the reason why this works in this multisim is because multisim needs a ground in order to calculate where all the other voltages are. Because this ground is a reference ground. That means from this point on, this is 0 volts and everything else is going to be higher than 0 volts,
right.
which technically means you don't need one here.
So essentially, there's a lower voltage or a
This is
different
always
voltage.
going to be 0 volts.
Yeah.
Like this is not 0 volts,
Right,
but this is always going to be 0. So multisim does a lot of calculations to compare everything to 0 volts.
Right.
Right? But this isn't, because in a regular circuit, you don't like specify where the ground is, essentially, right? In multisim, you have to specify the location of the ground because that gives it a place to calculate other things.
Yeah.
No, yeah, you put it here and it'll still work the same,
yeah.
right? But in multisim, you just need this here. Like if you don't have this, your circuit won't work. because it doesn't know where to put 0 volts.
It just has like knowledge of it, right?
Yeah,
Not only does this happen in Multisim, but P-Spice, you can't run it without ground. And I think LT Spice, you can't either. So
Yep.
in every simulation, you have to. Yeah. And sorry, I teach 2101. And so a good note that I like to tell students that is in DC. So this is all DC, right? A capacitor it's open, right? There's two plates. So it's a short. Or no, it's open. Sorry. It's an open. But an inductor, it looks like wiggle down, right? If you stretch that out, that's gonna be a wire. It's gonna be a short, right? So that's how I kind of, it's like a little hints that I kind of explain my students that like if you see a capacitor.
Inductors are just big coils of wire.
Yeah, and then you just stretch it out, then it's still wired, right? Any questions on this circuit? Yes?
Like why my the part that like running you see that one?
That,
I just like stay on 12 volt, but it's just like the like doesn't like going down when I like open the
yeah.
that F1.
Show her the negative V one. Okay. Any other questions?
It's not really about this circuit.
Oh.
The capacitors.
Capacitors?
Yeah, I've heard different things for capacitors. How many time constants do you consider a capacitor charge?
How many what?
In ECE, like how many time constants do you consider a capacitor charge?
Which is 1.
5? Okay, that's
5.
that's
Yeah. Tau is 5.
Yeah, so that's why I was just like, any precedent for you. So I was curious to see perspective was.
Oh yeah. Yeah, it's 5. Yeah. 5 tau. Oh my god, I haven't used it in so long. Okay. The voltage doubler circuit is a little okay. So we could either, do you guys want to do like AC or do you guys want to do like digital logic? AC? Do you guys want to play with more diodes or do you guys want to play with like the gates? Diodes or gates?
Openness to.
Diodes or gates?
So what this does-
Okay, I'm going with diodes then.
In fact, it has to be done charged. Open the component, open the S1 and close the S1. What this does.
You guys were able to run this, right?
Now,
You guys were able to get this to run?
it now senses.
Oh, okay, yeah. And then, okay. And then right here, like, I feel like, these are values that was charged.
The camera's bothering me.
And then you open it.
They're on the same node, it'll still be the same voltage.
Oh, these two? These two. If I wanted to run it, we never go to more than. Yeah, it was 9, but you guys, it was like.
There we go.
You have no problem.
My advice.
You need to build us a robot that like.
So just
takes
follow
this-
the-
Yeah, baseball, but you smart cascade.
Alright. The last challenge circuit. I built it already just because this is like circuits that you can find in a textbook. This, when you take analog, like microelectronics analog circuits, this is like one of the ones you have to know, right? So I'm gonna try to explain what is happening. There we go. And why. Should I explain this?
You have time.
Oh, I don't?
You have time.
Okay. So basically, you have an AC voltage that's 5 volts. If I can draw this, this would be the way. Okay.
No, are you on the Discord? I'll add you to this.
All right. So. Symmetrical. Pretend that's even. But, okay, so you have a 5-volt magnitude for the sine wave, right? So let's start off with this negative side, meaning that this is gonna be the other way, right? So let me just change this to this. So since it starts at negative, right? This means that it looks like this, right? Because earlier, this is 5 volts, and if you put negative, it means that like this, right? So when 5 volts going in, that means, and remember the current flows from positive into negative, right? So let's go. Go on an adventure, right? It can also go this way too. No, it cannot. Just this way, right? It hits this diode, 0.7. It depends. It's not always 0.7. So depending on your diode, it could be different. Yes?
So the positive, on the voltage below, not above?
Yeah, because right now we're at the negative side.
Okay, I just looks.
Oh, yeah.
And so, want to check.
Yeah, just pretend that's not there yet. Okay. So when it goes in here. So right now it's at 5 volts, right? And it goes through here. What should it be at? 4.3 volts at this node right here, right? And during this, it goes wait, yeah. And this is off because we can't go this way, right? This current is flowing this way. It can't go into, right? So right now, this is charging right now. Charging, like we just learned earlier, right? So that means that this is, everything goes into positive, out negative. So at this point, this is 4.3 volts. 4.3 volts is charging into this capacitor, right? Up to here, are we good? Yes. Okay. So when you put a battery together, 2 AA batteries, and you stack plus or negative plus, what has to be on top? What polarities first? Right? So it has to be negative plus, right? So now that we're in this mode right here, let me do this one. We're in the, where's my green? So now we're in the green mode, the positive mode, right? That means that this sign is now whoop, like that, right? So using that same battery concept, this is 5 volts. This is 4.3 volts, right? That means that at this point, right now, this should be 9.3 volts, right? Because the batteries are put together like this. And then it can't go down here, right? Because it's blocking it, but it goes through here now. So this is on 0.7 volts, right? Goes through, and this is gonna be 8 point, I don't know, off the top of my head. Yeah, 6 volts. And then it's charging this capacitor right here. Right? So now this is 8.6 volts plus minus. Right? Because current goes in the flow of plus to minus. Right? So if we put in 5 volts, your output will double, but not really, double out to be 8.6. If these diodes did not have the 0.7 drop, there will be exactly 10 volts, right? Because the only reason why this is 8.6 and not 10 is because of all these voltages you have to, take out, right? So this is one cycle. So through one cycle, you should be able to go from 5 volts to 8.6 volts. Now we're just gonna go through one more like this, right? Just to show you guys what happens afterwards. Afterwards, this will become a negative or positive and negative. So now this circuit is recharging, right? But this is off. So how is this still 8.6? Because of the capacitor that was charged up earlier, right? So there's always gonna be a constant 8.6 going out here, right?
It's
So-
not a perfect one though.
Yeah, it's like a like that. So if I run this circuit, right, 8.5 or 8.75, and then we got 8.6, which is like fairly similar, right? And the R1 is our load, because if I like, take it out, it'll give me like weird answers. So yeah. If you're electrical, you kind of have to understand the concept of this. Cause
It's essentially just built, it's around turning on through and then built.
yeah, it's this is putting together two of the concepts we learned today, right? Which is diodes going into one direction, going out the other direction, or not letting the other direction go, only one way. And we also learned about capacitors, energy, right? So this is the concept all put together. And this circuit is called a voltage multiplier. And in ideal way, in ideal mode, it would be 10. But because we have to consider the 0.7 and stuff like that, then it will bring down the voltages, right? And then I think we have time for one more, right? Oh yeah, 15 minutes. Okay. So this last one. Right. So the Hyperloop, the CPP Hyperloop protopod has two inputs, right? And depending on which, if you use the motor, if you brake, step on the brake, if you use the camera, or if you want to use all three of them, they all have a different color representing it, right? So this is now going into digital logic. So you have you have 4 states, right? Because you have 2 inputs. And you guys know why that is? Because 2 to the 2 is 4, right? So you have 4 different types of ways to put 2 numbers together. And then we have a red is 1, green is 0, blue is 0 for, you choose which state it is. All right, so how do we start this?
Maggie, you should let them figure it out.
Huh? Oh, you got this. Shawn,
You didn't draw the diagram, yeah.
Okay.
You might want to do a truth table.
Yeah.
Truth table, all right. So what is a truth table? A truth table tells you the truth of the circuit. So you have 1, 2, 3, 4. 1, 2, 3. Yes, that's fine. So
Yeah.
right. So you have input A, input B, right? And then you have RGB. RGB. Right? So this is your input 0, 0. When you put state 1, state 2, 0, 1, state 3, 1, 0, state 4. Right? And then for each state, you put in what you get. So 1, 0, 0. What's the second one?
1, 1, 0, 0, 0, 1,
1,
1, 1, 1.
All right. Yeah. So without using payments or anything, just make it easier, right? Well, I'll do one of them, and then you guys can try this later on by yourself. I'll do one. So my favorite color is blue. So we'll start with blue, right? So if I were to draw, man, I drew this way too big. Okay, so this is the blue. Right? So input A, input B, and B RGB coloring. So I'll rewrite down what it is. 0, 0, 0, 1, 1, 0, 1, 1. And we have B. 0, 0, 1, 1. Do we see any pattern between each column?
A must be on.
A and B have this. A and this B is the same, right? So if I were to do this, it's still the same, right, on both sides? What is B? Does it make? B is the third wheel that you don't want to be there. It doesn't matter why he's like, he doesn't need to be there. The true lovers are in. So what this is called is, what's it called? A is following B. Right? The input is what you're changing, right? So A is gonna be, or no, B is following. B is following, hold on. B is following. There you go. Because B is following what you're inputting, right? So that means that there's no logic gate being needed in this one, right? You can just put a wire, an A and a B, right? So just connect it straight. No, not A, not big A, small B, right? So at least for your RGB LED lights, it's one of those lights. You can just put A directly to B, right? So whatever you change, whatever, okay, whatever you change A to B, B will always be whatever it is, right?
So B is more than matter.
Yeah, B is don't care. That's what they call it, don't care, right? So using the same concept that I did, try to apply it with these other ones and see if you can get the circuit, right?
This is a real world application, by the way. I actually had to do this.
Yeah.
So you're doing something that's actually useful.
Yeah. This is also useful because like if in his case you're putting in like when I think of zeros and one, I think of switches, right? Or if you use a button, something like that. So sometimes you need to use like buttons to control. In his case, I think he controlled the pod, right? So it needs to know when it's like when you're using each thing, and that's what this is kind of telling us, right? Any questions? This is no K mapping. K mapping is a little more complicated.
This is logic.
Came out for fun.
Just logic it out.
Yeah.
Think harder.
Huh?
You not need infrared?
No.
No, this is tough, but you can do it. I believe in you. Oh, that's fine. Yeah, you can just look at it.
You remember the OR gate is a thing.
Oh, hint. Hint.
I actually use the.
This is annoying.
Okay, hi. Oh, this is Chris. And then. I'm gonna the gate.
There are multiple ways to do this.
Yeah, don't feel like you have to have one way, right? So.
If you're a computer engineer, you should play Chen complete. It gets you through like 8 of the 14 K. Like, I'm not joking, it actually does. Like, if you 100% the game, you'll be set for the rest of your computer engineering career.
All right, and then, yes.
Do assembly in double A.
Nah, you don't even touch assembly.
It doesn't teach you like power. For all I know.
Any question?
I love the
Yeah,
fact
oh,
that
go
the-
back.
I was-
Oh, yeah, no worries. And I think this should be posted on the server. Okay. For sure.
I like the fact that they learn how to do Python from like my very, very first workshop. It's still on the last slide.
Which one? Oh, this.
This last slide.
I had to get rid of that.
Oh.
I had to get rid of that one in the last line.
Oh boy,
I never removed.
This is a template, right?
Yeah.
Yeah.
Oh, now I see.
Yeah. You just apply that same thing, the same thing that I did, and you do it for all three RGB. Oh yeah, that would be nice kind of like.
You should do like behind this. Just do it for real.
Oh, of the circuit?
Why is it sticky? What? It's sticky.
What's the?
What's the-
How do I put this up?
Just last time. Wait, no.
Oh, put it down, put it down, put it down.
I'm writing the answers here.
Oh, wait, do you want, I have the answer on the simulation.
Oh, okay, you.
A multi-sim?
Never mind.
Okay.
It's fine.
Should I present it now?
No,
Oh, no.
just give them like 5 minutes.
Okay.
No.
In 5 minutes, I will show you guys the answer. And it running.
Your reward is that you can play with these. Current complete.
Turning.
You are.
Yeah, ing. Like turning on a car. Complete. Huh? Yeah. It's okay. If you don't know,
Pass this around. Spoiler.
if you don't know something, because I didn't prepare any of this. If you don't know anything, just skip it. Because I didn't even read all the slides. I was just like all in my head, what theory I knew, you know. So on your next, when you do another one, just put that in mind. Like you don't have to say everything because you're not the one making the slide. You know. So you don't want to be like, oh, I don't know.
Oh, sounds good. Oh, see.
Hi.
So the way that you figure this out, yes.
All right, I'm gonna show the answers.
About your results and your. Yeah. Done. I am.
Right. It's what? So, okay, yeah, let me No, very good. Okay. So you're talking about right here, right? You understood this part? Yeah, I'll go over, okay. So you have this. Okay, so right now, right, at the negative.
Yeah.
Negative means that so normally it's like, right, positive, but now that it's negative, so then this is positive, negative, right? So you're getting one volt going into here, because remember that it goes in the flow of positive, right? So it goes here. And it's in the middle, 0.6, right? So 5 minus 0.6 is 4. Oh, I'm sorry, hold on. 4.3. Yeah. Right? So, and this is gonna go into here. Because right now, this is, that means that it's gonna go back to positive, right? So you can't go this way. Yeah, so it's going in the flow to negative. So this is off. Okay? So it can go, and then even if it does go in here, it's going off this way. So it's trying to go into the negative, right? So then it's gonna go in here, right? That means that this is called like this is negative because the current flow is positive negative. And at this point right here, it's 4.3 volts, right? That means that 4.3 volts is charging this capacity. So through this whole, if I would probe it, this would be 4.3 volts. right?
Yes.
So now that's the first part. Now moving on to the second part. Imagine
Like go past because.
which one? Sorry. Uh-huh.
Like went in the opposite direction. Batteries heating up, that would be a short. Or is that one?
That's a short is when plus and minus touching. So like if you have a battery and you go like this, that's a short. But because it's like you're touching like positive, 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 positive. So even if it does go through here, it's still positive, right? Short is when you have no resistance. Like, I'm gonna explain it short. Like, the maximum current is going to the power. Because wires. I explain it short. But it this like I don't really know how to explain it short. So I asked an interview and I would not even know how to answer that question. Yeah, ask Chris. You probably know. But I short really. So earlier I explained that when my friend shorted the battery, it exploded. Because all like you're putting all the power into the other side, right? So that it like blows up. So try not to short. If you short, then it's pretty bad. But a lot of like a power supply, usually they have like a good power supply actually. Then they have like protection. So when you do short it, yes.
Do you need 150? Do you need?
I don't think so.
Okay.
Yeah. Good. Yeah. Okay, so now in this positive section, that means that this is wrong, right? Positive, right? So now we know taking this initial, this is negative plus. So right now, this is 4.3 volts, right? So if you put a battery together like this, that means that 5 plus 4.3 is 8.
So it goes. So what is the positive oh wait, positive goes to the negative.
Yeah. Yeah, like you put like the two batteries together, you have to like put it like this. Right. So that's basically just imagine a battery here and a battery, right? And obviously, this is the negative rail, right? Right now, this is the negative rail. So current cannot slow down here because it's blocking, right? So then it goes through here, right? And this is 0.7, this is 0.7. Sorry, a lot of the problems 0.76 too. And if you put 0.6,
Oh, I know it's supposed to be.
oh.
Maggie.
Oh.
Professor Maggie.
Oh, you're leaving?
Hey.
Bye.
Yeah, you're good at it.
Thank you. And then you go through here, this is 8.6, right? Because they drop, right? And you can't stop here because this is the output, but it's also going down to negative. So remember, this is all negative down here. This is positive. So it's as you're going down, this is charging it to 8.6.
We're into
Yeah. Now, this is why I needed the one more cycle, the one more loop, is because when you go back to the other way, right? So you here.
They forgot.
Hold on, if you forgot that the back to negative, or when it happens, I forgot to make it.
Good question, but no, because this part, So if you don't have it going back to positive, back to the source or the negative, then there's no current flowing. Because this right now is like, it's not there. It's just like a gleaming.
Yeah.
Yeah. And so you get to this point, right? This circuit is running, giving its motion to this one. But in this case, now this is 8.6 volts, with this being nothing, right? So if I were to close this, it would be 8.6 volts. But through this first one.
Oh, I'll text you wherever we're.
And this is happening, like, you know, so that's why, like, in the simulation, like, I won't, so it's like, it would be like this, but like super tiny, so it'd be like, which is technically a sine wave, but because it's so like, you would consider it, yeah. Go, it can't go this way. Yeah, that's why it's off. It's blocking. You can't. This is positive, 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 and it's trying to get to negative, which is negative, right? It can't. Yeah.
We're going to get the key.
CPP or the
Like in the route. Oh,
Yeah. So CPP engineering science. No. Software for students. And it's full teach them right. When you make your account, it will ask you for a serial number. Oh, I can show you this.
I have it downloaded.
Oh, it will be that serial number. Yeah. And then you just put it on there.
And I never started about.
I'm so tired. Are you taking what? Which one are you in? Oh, what the?
I'm in toys right now, like the satellite program. I'm probably gonna be doing that now because I just wanted to learn. I kind of like covered the basics of general. I forgot.
Yeah, no worries. Okay. Yeah, this is so like I don't do any of that. So last night I was like up to like 3 trying to figure that out. 'Cause I didn't understand. Well, I took it like a long, way too long. And then this is my specialty right here. That's why I kind of explained this one a little better than that. That's digital logic. Digital is 1 and 0. So you see it's all 1 and 0, and logic is like right? So digital logic.
Yeah.
I think
I'm leaving on.
analog. Analog is like
That's.
it's no longer 1 and 0. It's like everything. It's like an infinite. It's like when I'm talking to you right now, there's waves, you know? So there's like, it's not 1s and 0s anymore. It's not like on or off, you know? So that's different. I'm more the analog side because I work with like waves and stuff.
Yeah.
Yeah. Can you find it 1 and 0?
I'm breaking my back with these kids. Like Josh gave me stuff like straight.
Computer engineering.
Yeah.
Well, computer engineering is all 1 and 0. But oh, I hate digital. Oh, let me turn off the.
6 trillion other things.
That's cool how you're here and like, you know,
Our lab workshop was
where did it go?
That's what we did.